Did you, by any chance, take a drive yesterday? Maybe to your favorite store to do a little shopping? If so, did you take the exact same route to the store that you did the time before? I'm willing to bet that at some point in the past, you chose to take a different route for whatever reason. The question of the day is this: did it matter? When you take different routes from your house to the store, you ultimately arrive at the store. You're at the same latitude, longitude, and elevation regardless of the path you took to get there. We call properties like that state functions. State functions are simply defined as properties that are identical for all systems of a particular kind, no matter what has happened to them previously. If you drove over a mountain or through a tunnel to get to the store, at the end of it all, you still went from your house to the store. Last time, we saw how Berthelot gave us a way to measure the energy that changes hands when a chemical reaction takes place. Over decades, many scientists have used this device to measure the heats exchanged when many reactions take place. This allowed them to obtain a great deal of information about how energy flows when chemical bonds form and break. It took a lot of work and a lot of time to catalog the heats released and absorbed by various chemical processes. Now, wouldn't it be great if there were some way that we could get some of that information without having to actually run the experiment? See, each time the heat of combustion for a given material is measured, it's always found to be exactly the same. It doesn't matter if the reaction is run fast or slow, with large excesses of oxygen or just enough. It doesn't matter where the material came from or how it was made. For a given material, like our propane example, at the end of the reaction, the same amount of heat always changes hands. This apparently obvious fact is actually a crucial observation, because it means that just like our route to the store didn't alter our location when we got there, the route that a chemical reaction takes to its products shouldn't alter the energy that those products contain. This observation led to a law postulated in 1840 by a Swiss-born Russian chemist and physician named Germain Hess. He conducted a little experiment using a calorimeter, not unlike the one that we constructed last time. Hess was one of the first to realize that the enthalpy of any given system is always the same, no matter how it's made or what went into making it. In short, enthalpy is a state function. Now, Hess proved his idea using two very simple chemical reactions. The first of those is this. He reacted sulfur trioxide with water to form sulfuric acid, a very well-known reaction in his day. What was also known about this reaction is that it releases a certain amount of heat per mole of sulfur trioxide that is reacted. Now, Hess also ran another reaction. He knew that when he reacted sulfuric acid with, in this case, ammonia, NH3, in a 1:2 equivalence, he could make a compound called ammonium sulfate. And that in doing this, it also released a very well-known amount of heat. So what did Hess do that was so different? Well, Hess decided, instead of running these reactions separately, he would run them together in one pot. In other words, he would take that reaction and cancel out his sulfuric acids here and run a reaction where he added sulfur trioxide to aqueous ammonia, water and ammonia, so that the process could happen all at once instead of in a stepwise fashion, first making the sulfuric acid, then adding it to the ammonia. What he found was that when he ran the reaction this way, a certain amount of heat was evolved as well. But what was really remarkable was that it was exactly the summation of the heats of the two processes. The heat released when forming sulfuric acid from sulfur trioxide and then forming ammonium sulfate from sulfuric acid and ammonia was exactly equal to the amount of heat released when the whole thing happened all at once. And this prompted Hess to write that a combination taking place, the quantity of heat evolved is always constant, whether the combination is performed directly or whether it takes place indirectly and in different steps. And this famous experiment basically was the genesis of thermodynamics. It was when it was finally realized for the first time that heat is heat, and it adds up. We can break processes down any way we want, and then put them back together again, and the heats will always add up. So Hess's law states that the enthalpy change for a complex process is equal to the sum of the enthalpy changes of smaller steps making it up, no matter what those smaller steps may be. You may have taken the road over the mountain to the store one day, going up by hundreds of feet, then down again by hundreds of feet. Net change in altitude, 0. Another day you might have taken a flat road around the mountain. A different path to be sure, but still a net change of 0. Hess's law is important because it allows us to take a shortcut to predicting the enthalpy of a reaction by running that reaction in our minds, completely disassembling molecules to their constituent atoms, then putting them all back together into the products that we want to form. As long as we know the enthalpy changes associated with the smaller steps of our imaginary process, our result should translate to a meaningful enthalpy change for the reaction in the real world. This process would never happen in nature. In reality, chemical reactions take complex pathways of stepwise bond breaking and forming as they progress. But thanks to Hess's discovery, we can take a shortcut. Just like we could take any route we wanted from our house to the store, in our minds we can take any route from the starting materials to the products in our chemical reaction. We simply run an imaginary reaction, knowing that the enthalpies of the starting and ending points should be the same no matter how the process really takes place. One method that exploits that fact uses our knowledge of the energy released and absorbed when a typical type of chemical bond forms or breaks. We call these average bond enthalpies. So I'm going to make a catalog of those right now that we'll use off and on through the course. Let's start by thinking over here on the left about carbon and how it bonds to other things. Now, when a carbon atom and a hydrogen atom come together and form a chemical bond, 413 kilojoules worth of energy per mole of bonds is released. So that means that it would take that much energy to break it and reverse the process. What this means is that the higher the bond energy, or bond enthalpy is, rather, the higher the bond enthalpy is, the stronger the bond will be. So carbon-carbon bonds, not surprisingly, are pretty tough. They're 348 kilojoules per mole. Those are the bonds that are holding together the sugars in the foods that we eat and many of the molecules in our own body. Carbon-nitrogen bonds are a bit weaker and therefore a little bit more reactive. That's also not surprising. And if we continue looking through the halogens, we see that carbon-fluorine and carbon-chlorine bonds are fairly sturdy, which explains why they're used so often in refrigerants, which can escape into the atmosphere. We want to be sure that we use something that's not too reactive. Bromine and iodine, however, look how weak those bonds are. There's a very good reason that you don't hear about bromofluorocarbons or iodofluorocarbons. It's because they would be far too dangerous to the environment to use. And carbon-sulfur also bond with relatively low bond enthalpy as well, making it somewhat reactive. And we've got a whole laundry list of additional bonds that we can think about here. Multiple bonds release different amounts of energy. Notice that as I increase the bond order of carbon-carbon bonds, I go from a carbon-carbon single bond at 348 to a CC double bond at 614 kilojoules per mole. And it takes 839 kilojoules per mole on average to break a carbon-carbon triple bond, much stronger. And we see this trend continuing if we look through the table here at other bonds. We also have hydrogen, of course, is very common. And that bonds to a number of other elements as well. So we're going to want to consider occasionally just how strong hydrogen bonds with other elements. And so here's a list of a few of them now, and those will come to bear on some lectures later. But for now, we've got this very nice table with lots and lots of different bonds in there and their average bond enthalpies. So how is it that Hess's law gives us a way to use these apparently disparate energies here? I mean, they're all different bonds, right? How do we use this in a way that lets us calculate how much energy changes hands when a molecule converts from one type to another? Well, we do this because Hess's law allows us to take a set of reactants, convert it into anything we want to in our minds, and then convert that into the final product in a two-step process. Then combine the heats that we expect to determine the overall heat of the process. For example, here's our combustion of propane yet again. We know this reaction very well now. Propane and oxygen combine in a 1:5 molar ratio to form carbon dioxide and water. But if I wanted to predict the heat of this reaction rather than measure it as we did with our calorimeter, how would I do that using Hess's law and bond enthalpies? Well, again, Hess's law lets me say, you know what? To know the delta H for this reaction, I can take propane and oxygen and do absolutely anything I want to it. I can turn it into atoms. I can atomize it, break every single bond in the propane, every single bond in the oxygen, and create gas phase atoms in my mind. And then use those gas phase atoms to rebuild my products, forming all the bonds that make them up. So if I were to employ this strategy, I might write my reaction out like this, with an intermediate condition where I have oxygen atoms in the gas phase, hydrogen atoms in the gas phase, and carbon atoms in the gas phase. Something that we would probably never actually observe in a reaction like this, but that doesn't matter because of Hess's law. So I'm going to do this because Hess says I can. I'm going to atomize my starting material and then rebuild my product completely from scratch. So when I do this, I'm going to break a certain number of bonds, right? And then put my atoms back together and form a new inventory of bonds. And simply by taking the bond enthalpies and doing a little bit of accounting, I'm going to be able to determine roughly what the energy of this reaction will be, or the enthalpy of this reaction will be. So let's do that now. So the enthalpy for this reaction is going to be simply equal to the total amount of enthalpy required to break every single bond in the starting material minus the total amount of heat that it is released when every single molecule of my product is formed. I can get these numbers from my bond enthalpy table. So going to my bond enthalpy table and doing a little bit of accounting, I find that I have 2 moles of carbon-carbon single bonds in propane. You can see those right here. 1 carbon-carbon single bond, another carbon-carbon single bond. I've also got on that same molecule a grand total of 8 carbon-hydrogen single bonds. And I know what those average bond enthalpies should be. Additionally, I need enough oxygen for that combustion to take place. So I'm going to have to also account for the fact that I've got 5 moles of oxygen-oxygen double bonds, also available in my table. So if I do the math, what I discover is that all of the energy that's required to break all of those bonds is equal to 7,171 kilojoules, approximately. So that's half my equation. I now know how much energy would be necessary to completely tear my molecules apart into their constituent atoms in the gas phase. Now, the following step is to take those atoms in the gas phase and rebuild my products. So let's do that over here on the other side. The enthalpy of bonds formed would be 6 moles of carbon-oxygen double bonds because I've got 2 per molecule, and 8 moles of OH single bonds, also from my waters, which each have 2 of those bonds. I go to my table, I get my numbers, and I discover that the amount of heat released when all of these bonds form is 8,506 kilojoules approximately. So now I have the total amount of energy needed to break all of the old bonds and make all of the new ones. I simply combine those to determine the heat of the overall process, which is allowed by Hess's law. So the heat for this reaction is expected to be 7,171 kilojoules minus 8,506, with the signs letting me know which bonds are broken and which were formed, for a total of minus 1,335 kilojoules per mole of propane. Not exactly the number that we got in our experiment, but certainly a good estimate. But using average bond enthalpy suffers from the problem that we're dealing with averages. Not all carbon-hydrogen bonds are identical. So some are slightly higher in energy, some are slightly lower, and our slightly deviant value here is a testament to that. So average bond enthalpies are just that, an estimate of the amount of heat released when a bond forms or absorbed when it's broken, determined by averaging out the observed enthalpy for a particular type of bond over a range of situations. But not all bonds between 2 particular atoms are created equally. For example, the energy required to break the OH bonds in water are actually not identical. Breaking the first bond requires slightly more energy input, about 499 kilojoules per mole, and breaking the second slightly less, about 428 kilojoules per mole. Close to one another, but different enough to possibly be important. Our estimate of the heat of combustion of propane is a testament to that inaccuracy. We missed by nearly 1,000 kilojoules per mole. Using average bond enthalpies is great when we only need an estimate for the energy released in a reaction, because there are relatively few combinations of 2 bonded atoms. This makes for a very manageable table of values that we have to scan through. But what about when we need more precise numbers? Well, sometimes we have to bite the bullet and actually use an enthalpy value specific to the compounds that we're studying. But what value to use? We need something easy to compare from molecule to molecule. But what process might that be? Now, remember that absolute enthalpies are actually impossible to know. We have to compare the enthalpy of a product to that of a set of starting materials if we're going to determine any kind of change whatsoever. But those starting materials can be anything we want to imagine. So, how do we choose? Well, why not choose something simple that we can all remember and agree on? How about pure elements in their standard states? It seems like the most logical place to start. This is exactly what chemists do. We arbitrarily define the enthalpy of any element in its standard state as 0. Now, measure the heat gained or lost when a compound of interest forms from elements in their standard states, and call this value the heat of formation for that compound. Here are a few heats of formation of some elements. H2 gas, 0 kilojoules per mole. O2 gas, also 0 kilojoules per mole. Carbon as graphite, 0 again. Now, how about carbon as diamond or oxygen as ozone? Trick question, right? Diamond and ozone may indeed be pure carbon and oxygen respectively, but they're not in the standard state. Ozone and diamond aren't the most stable form of these elements at standard temperatures and pressures. So diamond actually has a non-zero heat of formation. Simply rearranging the atoms in graphite to form diamond actually requires the input of a small amount of heat, about 1.9 kilojoules per mole of carbon. And turning diatomic oxygen into ozone requires the input of 143 kilojoules per mole. So ozone is clearly much less stable than diatomic oxygen, a fact we've predicted many times in the course. So now that we can spot elements in their standard state and realize that their enthalpies are arbitrarily set to 0 for comparison, we can measure the heat change when any compound we can imagine is formed from its constituent elements in their standard states and assign that value as its heat of formation. We can estimate the heat of reaction of the combustion of propane instead of using bond enthalpies using heats of formation, using this equation here. Now, I need to point something out that's very important right now because it's easy to get lost in the signs here. Notice that in this case, the heat of formation of the products is positive and the heat of formation of the reactants is negative. So you'll often see this equation written as heat of formation of products minus heat of formation of reactants as well. In either case, mathematically, they're equivalent. Now, I've written them this way so that we can illustrate exactly how this is possible. Again, let's consider our reaction. Propane and oxygen react to form carbon dioxide and water. And because Hess's law says I can choose any intermediate I want to, instead of atoms, I'm going to choose elements in their standard states, those states in which they're found on the surface of the Earth at about room temperature and pressure. So in this case, I'm going to take my propane and oxygen here, C3H8 and O2, and I'm going to convert it into the products CO2 and H2O. But my intermediate for this calculation is instead going to be carbon as graphite, hydrogen gas, and oxygen gas. These are the standard states, and remember, they're used in determining the heats of formation of any substance. So essentially what I'm doing here is I'm going to take my reaction, take my starting materials, and run the exact reverse of their heat of formation reaction, forming elements in their standard states. Then I'm going to run the reaction in the forward direction to form my products from elements in their standard states. Therefore, I can assume that the heat of the overall reaction is simply equal to minus the heat of formation of reactants, because we're going backwards, plus heat of formation of products, because that portion of the reaction is the heat of formation going in the forward direction. Let's get our best estimate yet at the heat of combustion of propane using heats of formation. We have to consider 4 reactions, really. The first of those is propane being converted into graphite and hydrogen. Again, this is the reverse of the heat of formation of propane. Now, oxygen is an element itself in its standard state, so we can write a reaction out like this, although it really means nothing is happening as far as the oxygen is concerned. We're also going to consider the formation of CO2 from its elements in their standard states and the formation of water from its elements in their standard states. The reason I'm considering these is, again, Hess's law allows me to combine these reactions, canceling out those things which appear on both sides, and create the overall reaction that I'm going to be analyzing. Here it is, the combustion of propane, perfectly balanced. Meaning, if I were to take the heats of all four of these processes and then combine them, I should get the heat for the overall reaction. So let's get those numbers now. We're going to use 1 mole times the heat of formation of propane because we have 1 mole. It's got a negative sign on it, of course, because this reaction's gone backwards. In the case of oxygen, it would be -5 times its heat of formation. But of course, that's 0, so it becomes kind of pointless. However, the others have got to be there. We need +3 times the heat of formation of CO2, because that's going in the forward direction, and +4 times the heat of formation of water. All numbers that I can easily get from a table. And when I go to those tables, I get these numbers. Simply doing the math leads me to the conclusion that when I subtract the heat of formation of reactants from the heat of formation of products, I get 2,046 kilojoules per mole. A very reasonable estimate for the heat of combustion that we determined previously. So heats of formation for various compounds give us a way to even more accurately estimate exactly how much energy changes hands, not just in the combustion of propane, but in a variety of reactions. And it all hinges on the ideas of Germain Hess, published more than 170 years ago. So let's review what we've covered in this lecture. We started with an introduction to Germain Hess, a Russian chemist who was the first to realize that enthalpy is a state function, meaning that heat change for a complex process is equal to the sum of heat changes of all of its individual steps. Next, we took a look at how chemical bonds can act as vehicles for energy, storing and releasing it as they break and form. And we saw how Hess's law allows us to use an inventory of all the bonds broken, formed in a process, to estimate the enthalpy change associated with reactions like the combustion of hydrocarbons. Then we took a look at a somewhat more accurate technique for estimating enthalpy changes, using heats of formation. Since actual absolute enthalpy can never be known, we simply agree on a standard of enthalpies, making all elements in their standard states equal to 0 kilojoules per mole. We then use the heats of formation of materials, measured when they are formed from their constituent elements in their standard states, to get a much more accurate estimate of a reaction's enthalpy. All of these tools for predicting and measuring enthalpy changes in reactions will come in very handy as we move forward, giving us ways to track heat as it flows into and out of chemical systems. But heat or enthalpy is not alone in driving chemical reactions and processes. To continue our discussion, next time we're going to have to consider another property of matter, one less familiar to most of us. Next time, we're going to be discussing disorder. Now that we've had some time to consider the fundamentals behind thermochemistry, let's apply our understanding of that to a new challenge problem. Now, most of us are familiar with military rations. If you're intimately familiar with them, then you've actually eaten them, and I apologize for that. But our problem is actually going to surround a very important technological development that helps make those meals a little bit more edible if you happen to be in the field. Here's our problem. In 1995, the U.S. military wanted to create a better heater for their rations that they sent into the field with soldiers. Now, they needed a heater that could produce enough energy to heat a half a pound of food, which is what's contained in a standard military ration, by 56 degrees centigrade, in order to be sure that the meal was warm enough that it was safe and at least somewhat decent to eat. So, a number of different companies set to work immediately trying to develop the next great heater that could deliver the appropriate amount of heat to do this task without using a flame. Because of course, if you're a soldier on the battlefield at night, the last thing you want to do is cook your food over an open fire and make your position well known to the enemy. Now, the company that eventually won this little development war used this reaction right here. The reaction of magnesium metal with water. Something so simple that the soldier will have them in their canteen. All they have to do is add water to this magnesium metal, and they can produce heat in a reaction that does not create a flame. It does create magnesium oxide in solid form, hydrogen gas, which can simply escape into the air, and again, a certain amount of heat. So let's work our problem here, assuming that the food inside of a ration is roughly the same as water as far as its ability to absorb heat, meaning it has the same specific heat, and that about 1/3 of the heat that's produced by a ration heater will actually get absorbed by that food. So using these numbers, let's figure out, if we're developing this new product, exactly how much magnesium metal does a soldier have to carry with them to warm up a day's meal. Right? If it turns out to be pounds and pounds, then maybe we're going down the wrong path here. So let's begin by calculating the amount of heat required to heat 228 grams of water by 56 degrees centigrade. We're going to use our mass, right, our specific heat, and our desired change in temperature to calculate heat. Right? Q equals mc delta T. Now this calculation lets us know that it takes 53.4 kilojoules to heat up that amount of water by that specific temperature that was requested. Now our next goal is to think about the reaction that we're proposing that we use, magnesium metal with water. How much heat will 1 gram of magnesium create in this particular reaction? Now to do that, we have to go to some tables. Right? So we'll go to our tables and we find the heats of formation of these materials. Right? Here's the heat of formation of magnesium, 147.1 kilojoules per mole. The heat of formation of water at negative 285.8. Of course, hydrogen gas is a pure elemental substance, so that's 0. And the heat of formation of magnesium oxide, we're going to use negative 601.8 kilojoules per mole. Now remember, to get the total heat change in a reaction, we simply apply Hess's law and use the heats of formation of all of the products minus the heats of formation of all of the reactants to get that number. So let's put those numbers into our equation and see what we get. In this case, the reaction is balanced nicely. It's all coefficients of 1, which makes the math fairly straightforward. We can calculate that the overall heat change in this reaction for 1 mole of magnesium is equal to minus 463.1 kilojoules. But that's kilojoules per mole. And we live in the real world where we don't count atoms of magnesium out. We want to weigh them on a balance when we're creating our product. So let's convert that from kilojoules per mole of magnesium into kilojoules per gram of magnesium using magnesium's molar mass and a little bit of unit analysis to be sure that our equation is set up correctly. Here I'll get kilojoules per gram of magnesium, minus 19.05. So 19.05 kilojoules of energy are released when 1 gram of magnesium reacts by this reaction that we've got here. So remembering that we've got a system here where only 1/3 of the heat generated will be absorbed by the food, we need a heater that's going to emit 160.2 kilojoules of heat. And we just determined that using the reaction we propose, we can get 19.05 kilojoules of heat released per gram of magnesium metal used. Which means that in the final analysis, we're going to have to use 8.4 grams of magnesium metal. That's about 1/3 of an ounce, or about the weight of 2 nickels. Well worth carrying in your pocket if it means a hot meal in the field.